On February 3rd, 2022, a SpaceX Falcon 9 rocket lifted off from Kennedy Space Center carrying 49 brand new Starlink satellites, each one designed to beam internet down to homes across the planet. Within 24 hours, almost all of them were gone. A geomagnetic storm, triggered by activity on the surface of the sun days earlier, puffed up Earth's upper atmosphere just enough to nearly double the drag on the satellites orbiting at a low altitude. Engineers watched helplessly as up to 40 of the 49 satellites lost their fight against gravity and burned up in the atmosphere, a loss estimated at around $100 million, gone in a matter of days because a star 93 million miles away sneezed. Engineers at SpaceX had no real time to react. The storm hit fast, the atmosphere puffed up before anyone on the ground could adjust the satellites' orientation enough to save them, and by the time the dust settled, the mission had gone from a routine launch to a multi-million-dollar cautionary tale about just how little control we actually have over what the sun decides to do. If a distant flicker of solar activity can wipe out a fleet of satellites without warning, what else is our sun capable of, and how well do we actually understand the giant ball of fire we orbit every single day? The uncomfortable truth is that almost everything you think you know about the sun is either incomplete or flat out wrong. And some of what scientists have discovered about its temper, its colors, and its possible siblings out there in the dark is enough to make you look at the sky a little differently. Let's start with something that sounds almost too strange to be real. Did you know the sun is technically green? No, this isn't a joke, and no, you're not being pranked. In reality, the sun blasts out every visible wavelength of light simultaneously. Red, orange, yellow, green, blue, violet, all of it, all at once. So where does color even come from? Rainbows happen when sunlight passes through water droplets in the air and gets split apart into its individual wavelengths, letting our eyes pick out each color separately. That's actually the sun's real color. Astronauts aboard the International Space Station, looking down through no atmosphere to distort the light, see the sun as a blinding white sphere, not yellow at all. So why does it look yellow, or sometimes orange or red, from the ground? Blame the atmosphere. Air molecules scatter short, wavelength blue light in every direction far more efficiently than they scatter the longer red wavelengths, a phenomenon called Rayleigh scattering. That scattered blue light is why the sky above you is blue right now. It also means that by the time direct sunlight reaches your eyes, a chunk of the blue has been stripped out, shifting what's left toward yellow. During sunrise and sunset, when light has to travel through a much thicker slice of atmosphere at a low angle, even more blue gets scattered away, leaving only the long red and orange wavelengths to survive the trip, which is exactly why sunsets glow pink, orange, and red. Now here's where it gets fun. What if the sun actually was red instead of white? Picture this. Every waking moment of your life would look like a permanent sunset. Crimson skies at noon, orange oceans, a blood-red moon reflecting it all back at night. It would be dimmer than what we're used to, sure, but survivable, even beautiful in a strange way. And here's the twist. This isn't just a thought experiment. In roughly 5 billion years, our own sun will actually become red as it dies. Once it exhausts the hydrogen fuel in its core, it will swell dramatically and transform into a red giant, engulfing Mercury and Venus, and possibly reaching all the way to Earth's orbit before it's done. Thankfully, none of us will be around to see it. What if the sun were green, since we already established that it technically contains a strong green wavelength? The peak of the sun's emitted spectrum actually does sit in the blue-green range. If Earth's atmosphere somehow filtered out every other wavelength and let only pure green through, the entire world would take on an eerie emerald tint, and everything would be noticeably darker, since green sits in the middle of the visible spectrum and carries less overall energy reaching us than the combined white light does. Not the easiest color to adjust to, and definitely not as photogenic as it sounds. Blue is next, and this one comes with a twist that breaks our everyday intuition. In everyday life, we associate blue with cold and red with hot. Think of a blue flame versus a red one on a stove. But in space, the logic flips completely. Blue stars, called blue giants, are the hottest, most massive, and often the youngest stars in the galaxy, some burning at surface temperatures exceeding 50,000 degrees Fahrenheit compared to our sun's roughly 10,000 degrees. Red and orange stars are actually the coolest. If our sun somehow turned blue, oddly enough, we might not notice much difference in daily life because, remember, the atmosphere already scatters blue wavelengths aggressively. The sky might deepen into a richer blue, but the overall picture from the ground would look surprisingly familiar. Now for the darkest possibility of all, a black sun. If the sun simply switched off, humanity would have no more daylight, no more moonlight, since moonlight is only reflected sunlight in the first place, and no way to see the moon at all. We'd be left relying entirely on starlight and whatever electricity we could generate. This sounds purely hypothetical, and true black stars, meaning completely burned out husks with zero light output, don't currently exist anywhere in the universe. But here's the unsettling part. They will exist eventually, and our own sun is on that exact path. After the sun finishes its red giant phase, roughly 5 billion years from now, it will shed its outer layers and collapse into an incredibly dense, glowing ember called a white dwarf, an object packing nearly the mass of the sun into something the size of Earth. White dwarfs no longer generate energy through fusion, so they simply cool down extremely slowly over unimaginable spans of time, eventually becoming what astronomers call a black dwarf, a cold, dark stellar corpse. The catch is that this cooling process takes an estimated 1 quadrillion years, and the universe itself is only about 13.8 billion years old. In other words, the universe isn't even 1/10,000th of the way to old enough for a single black dwarf to have formed anywhere, not once, in the entire history of everything. Every so-called dead star out there is technically still emitting a faint glow. If our sun somehow instantly turned into a black dwarf today, the consequences would be catastrophic, but not instantly fatal. The solar system would plunge into total darkness immediately. Surface temperatures on Earth would crash to around freezing within moments, then keep falling, roughly halving every 2 months, according to thermal modeling of a sunless Earth. Within a year, surface temperatures could plummet to nearly 450 degrees below 0 Fahrenheit. Photosynthesis would stop instantly, killing off plant life that depends directly on sunlight within days to weeks, though trees, with their slow metabolisms and ability to draw some nutrients from soil, would likely survive far longer than smaller plants. The upper layers of the oceans would freeze solid within a relatively short window, but that ice crust would actually act as an insulating blanket, protecting the deep ocean from freezing completely for a much longer stretch of time, meaning deep sea creatures, already adapted to extreme pressure, cold, and darkness, would likely be the last complex organism standing. For humans, the immediate danger wouldn't just be cold. Without sunlight, our bodies would stop producing vitamin D and melatonin properly, throwing sleep cycles and immune systems into chaos. Realistically, survival would mean burrowing toward Earth's core heat, which sits above 9,000 degrees Fahrenheit, or clustering near geothermal hotspots like Iceland or active volcanic regions, where residual planetary heat could sustain small pockets of life for a long time, likely in giant sealed habitats or deep ocean submarines built to hold onto whatever scraps of warmth remained, slowly adapting to permanent darkness the way certain deep sea creatures already have. So the sun's color isn't fixed or simple, and its ultimate fate is written in stone. But right now, today, in 2026, the sun isn't dying. It's doing something almost the opposite. It's waking up, and that waking up has consequences we're only beginning to fully grasp. Every 11 years or so, the sun cycles between a calm phase and a violently active phase, and every 22 years, it actually flips its magnetic poles entirely, a feat Earth hasn't managed even once in the last 600,000 years. Scientists still don't fully understand why the sun's cycle runs on this rhythm. What we do know is how to measure it, mainly by counting sunspots, those darker, cooler patches on the sun's surface caused by tangled magnetic field lines suppressing the flow of heat from below. They only look dark by comparison. Since even a sunspot is still blisteringly hot, it simply looks dim next to the far brighter surrounding surface, much like a lit candle looks dark next to a spotlight. Sunspots tend to form in magnetically linked pairs, one positive, one negative, with looping electric currents of ionized gas arcing between them. The more sunspots visible on the sun at any given time, the more active and unstable the sun currently is. For roughly 100 years leading up to the past decade, the sun had been unusually calm, so quiet that scientists began worrying its typical active calm rhythm was breaking down into something more like active calm. Then came solar cycle 25, the 25th complete 11-year cycle recorded since scientists began systematically tracking sunspots back in 1755. NASA's official forecast predicted this cycle would be another mild one. Instead, it dramatically overshot every prediction. Sunspot counts blew past forecasts within the first couple of years, and by the time the cycle approached its peak around 2024 and 2025, it had become one of the strongest solar cycles observed in decades, catching much of the scientific community off guard. Even now, moving through 2026, activity remains elevated compared to the muted cycle before it, and forecasters are still watching closely to see exactly how slowly this particular solar temper tantrum settles back down. This matters because solar activity isn't just a pretty light show, it directly threatens the technology our entire civilization depends on. When magnetic field lines around sunspots twist, stretch, and finally snap, they unleash solar flares, sudden intense bursts of radiation that blast out at the speed of light. Flares are ranked by intensity using letter classes. C-class flares are minor and barely register on Earth. M-class flares are strong enough to occasionally trigger spectacular auroras near the poles. X-class flares, the most powerful category, can cause radio blackouts across entire continents. damage orbiting satellites, expose astronauts and high-altitude airline passengers to elevated radiation, and, in extreme cases, threaten power grids on the ground. But flares aren't even the biggest explosions the sun produces. That title belongs to coronal mass ejections, or CMEs, colossal eruptions from the sun's outer atmosphere, called the corona, that can hurl 1 billion tons or more of magnetized plasma out into space at speeds up to a couple million miles per hour. The corona itself is one of the strangest mysteries in solar science. While the sun's visible surface runs around 10,000 degrees Fahrenheit, the corona surrounding it, which should logically be cooler since it's farther from the energy source, is instead somewhere between 1 and 2 million degrees, occasionally spiking even hotter. Nobody has fully solved why, and it remains one of the most stubborn open questions in modern astrophysics, one that has kept solar physicists arguing for decades. One leading theory suggests the corona is heated by intense magnetic waves and acoustic vibrations rippling up from the sun's turbulent interior, essentially meaning the sun rings like a bell, oscillating with millions of distinct sound wave frequencies, in a field of study astronomers call helioseismology, borrowing the same basic principle seismologists use to study earthquakes here on Earth. An international scientific collaboration called GONG, the Global Oscillation Network Group, uses observatories spread across multiple continents to monitor these solar vibrations around the clock, tracking the sun's internal rumblings in real time. When a coronal mass ejection slams into Earth's magnetic field, it can trigger a geomagnetic storm severe enough to overload transformers, scramble GPS signals, disrupt radio communication, and, in the worst-case scenarios, take down power grids entirely. This isn't hypothetical fear-mongering. It has already happened. On March 13, 1989, a powerful coronal mass ejection struck Earth's magnetosphere and knocked out the entire Hydro-Quebec power grid in Canada within about 90 seconds, plunging 6 million people into darkness for roughly 9 hours in the dead of winter, freezing pipes, stranding people in elevators, and shutting down Montreal's subway system in the middle of rush hour. And, in September 1859, an even more extreme event known as the Carrington event sent telegraph systems across Europe and North America into chaos. Some operators reported their equipment sparking and catching fire, even after being disconnected from power, because the storm was strong enough to induce electrical currents directly into the wires. That same storm lit up auroras so bright and so far from the poles that people in Cuba and Hawaii reportedly saw the sky glow, and some campers in the Rocky Mountains apparently woke up in the middle of the night and started making breakfast, convinced the sun had already risen. If a Carrington-level storm struck today, with our reliance on satellites, the internet, and interconnected power grids, experts estimate the economic damage could run into the trillions of dollars and take months or years to fully repair, since replacement transformers for large power grids are often custom-built and can take well over a year to manufacture and ship.